So, good evening, everyone. Today's session will be on numerical schemes and solvers. So, first, we will just go ahead with all the numerical schemes and all the options that are there available. And then I'll briefly show you about where exactly are the solvers or the code for the solvers located, and how can you actually open those and copy those into any folder that you want for a modification purpose. But we won't go too much into the modification part because we have a session for solver modification in itself. So for now we'll only see the numerical schemes and briefly about the solvers. Okay, now over the past few weeks you all must have gone through the basics of OpenFOAM. Then we went through structured, unstructured mesh. After that, we also had a session on boundary conditions yesterday. So you are familiar with the case structure of OpenFOAM, right? So just briefly to touch upon this, we have the zero folder. That is where you would specify your initial and boundary conditions. In this case, we have the icofoam directory. So we just have velocity and pressure. For turbulence modeling, you might have additional parameters or additional files as well. But in this case, it's pretty simple for the icofoam case. Then we have the constant properties. This is where you would specify all the properties that remain constant. And you also saw that for block mesh and for snappy hex, in snappy hex, you would have an additional folder known as tri-surface. That is where you would add your geometry or HTL file. But again, in this case, you won't have that because it's the icofoam case, pretty simple. And lastly, you have your system folder. That is where you would specify your simulation parameters. In this, you have your block mesh dict, control parameters, and all the other things that are necessary for running your simulation correctly. Now, along with this, within your system folder, you will have a file named FV schemes. Now, this is the file where you will specify all of your numerical schemes or anything that is important to solve, or the mathematics behind all of your CFD simulations. So the keywords that you specify for each of these will be specified in your FB schemes. Okay. So to begin with numerical schemes in CFD, you would have to first understand the numerical schemes that are typically used in a CFD simulation. That's not particularly in OpenFOAM, but just in CFD as a whole. So over here we have a general conservation equation. In this you have your density terms on the left. Now, if you were to simplify this, say, let's say we take the mass conservation equation, and we also know yesterday Pranay also mentioned something as partial derivative equations. So in CFD, we use these derivatives. So we'll look on this ahead as you move forward. So let's take that mass conservation equation and we will be integrating it in FVM. Now, FVM over here stands for finite volume method. He also mentioned yesterday, Pranay mentioned that there are some methods known as finite element method and finite volume method. Now, the entire OpenFOAM framework is based on the finite volume method. So over here, we're integrating it in that sense. So again, over here, we had the mass conservation equation. Taking that, we are integrating it in terms of volume and with respect to time. So on the left-hand side, you have the density terms that are integrated. So this, if you take this particular equation, you can't directly solve it. Like computers can't understand what you're trying to do because there are too many variables, there are many things going on. So to simplify it, we will first, on at least the density terms, we will first integrate that with respect to time. So we have the simplified version of the density terms itself. And again, when you integrate it with volume, you will have this particular equation at the end. So on the left hand side, you have density, and then you have also your volume term, and then you have the remaining terms of your equation. Now, if I take that end equation that we have, okay, now the very first term that you have, that is your density and volume terms, that is in the order, in your second order FVM, that is a finite volume method. And in this particular term, your density will remain constant, or we specify or assume it to be constant for using it in CFD packages. Now, most CFD packages will use this approximation. For incompressible flows, it is typically used. And in OpenFOAM also, these approximations are used in your FP schemes. Okay. Now, there are multiple things that you have to know before actually specifying all of these schemes or the numerical schemes that are there. So for that, you have a CFD course. You will learn in that. If you haven't learned yet, If you have learned it, then you will relate to this equation. And another reason that we say that open form is limited in terms of incompressible flow only, it is because of these approximations itself. So if you were to run something like a hypersonic flow or something that is in the compressible regime, open form will not perform that well as compared to any other software. You would have to use some add-ons or some additional files that will have pre-compile it, or there are already on GitHub multiple solvers specifically designed for compressible flows. This is the very reason, because the entire OpenFOAM framework is based on the incompressible equations or the incompressible schemes. So if you want to dive deeper into compressible flows, you would have to tweak a few libraries here and there or modify some of your solvers. That is why I said that you have numerical schemes and solvers go hand in hand. Now, another thing to keep in mind when dealing with schemes or any other parameter, you have one term that is your accuracy and you have another term that is your stability. Now, these two are inversely proportional to each other. So if one increases, the other one will decrease. In this case, in case our accuracy is increasing, your stability will decrease. So you have to find a sweet spot between accuracy and stability. For this very reason, we have multiple schemes, and we'll dive deeper into that as to what scheme is accurate and which one is stable. Okay, so let's keep that in the corner for now, so that you know during the entire thing that as accuracy increases, stability decreases, or vice versa. Okay, so to begin quickly, I'll just open one of the FE schemes files. So I showed you the location, right? So this is your cavity case, the lid driven cavity case, the very first case that you did. So in this, we have the FE schemes located in your system, and then you have FE schemes. So over here, you have to note down there are a few headers, okay, or you can take as a you can say as a head, like headers, proper headers that you would have to keep in mind when dealing with the FE schemes options. So you have the very first thing as DDT schemes, you have grad schemes, you have div schemes. So all of this will look in detail during the presentation. We also have Laplacian schemes, interpolation schemes, and in the end you have SN grad schemes. Okay, so just keep in mind when we are looking at these syntax or these blocks during the whole presentation. Okay, because I've broken them down into individual blocks, explained each and every term and whatever options are available in OpenFOAM for each of these blocks. Okay, so going back to the presentation. Yeah, so the very first block that we have, okay, is your DDT schemes or your derivative schemes. Okay, now this particular block is where you will add all of your derivative schemes. Okay, within this you would have two keywords, default and Euler. Okay, now it's not necessary that it will always be Euler, it will be something else. I'll talk about that later. So the very first keyword that you have is your default keyword. This particular keyword will specify that whatever setting you're giving for this derivative scheme, it has to be run for every derivative, or for every set, for everything you are setting up this particular derivative or derivative scheme. And if you look at this particular block, you will get an idea whether your simulation is going to be a transient simulation or it's going to be a steady state simulation. I'll get back to that again in the future. The next thing we have is the Euler or the Euler keyword. Okay, now this is your derivative method. So we saw that you have multiple derivative methods. Now this method, the Eulerian method, is a first order integration method. So it's, in terms of accuracy, it won't be as accurate as a second order scheme that you're going to be selecting, but it is stable enough. Okay, so there are some compromises that you get when using this particular derivative scheme. And now some of you may ask, what are the other options available? So in OpenFOAM 24, there are a few. There might be more than this. I've just listed out a few common ones. So the very stable ones are on the top, and you have the accurate ones at the bottom. So the very first one, you have the first three on the right hand side over here. You have the Euler, you have Crank-Nicholson, and you have backward. Now Euler, as I said, it's a first order scheme. So in terms of stability, it is stable enough, but not that accurate. The next one you have, that is a second order scheme, that is Crank-Nicholson. Now with Crank-Nicholson, you'll also have a numbering scheme. Now you can change this number between 0 to 1. If you set it to 0, it will behave similar to Euler. And if you set it to 1, it will give you pure Crank-Nicholson results. So you will have good enough results, and but your stability, you'll have some random oscillations and also you have to keep that in mind. So keeping it at 0.9, you will get somewhat stable results. You'll have an accurate result as well. You also have backward DDT scheme. You can use that, but again, when you're specifying each of these schemes, you need to know what you're doing. Otherwise, you will get wrong results. You won't get wrong results, but some of your simulations might take time. They might crash. They might give some problems. Okay, so your stability goes to a toss. So when you're choosing each of these schemes, so you have to make sure that you know what settings you're specifying beforehand. Another thing that you'll see down over here is your steady state. So if I were to open the simple form case, you will see that in simple form FE schemes, you have something known as a steady state scheme. So this steady state is it just sets all of your time derivatives to 0 in very simple terms. So, so looking at these things, so if you see Euler or you see Crank-Nicholson or you see backward, you can get an idea that those simulations are going to be transient in nature, whereas your steady state, if it is mentioned over the specifically steady state, so that is a way you can gauge that it is going to be a steady state simulation or a transient simulation. Okay, so if you are not sure what are you solving for, you can always open your FP schemes and check the DDT schemes under that, what is it specifying. Okay, yeah. Now moving on to grad schemes or your gradient schemes. Okay, now your gradient scheme, this particular block is where you will add all of your methods for approximating your gradient integrals. And the very first keyword, again, you have default. So this is the approximation that will be used for every gradient, whatever setting you specify for this. If you have not specified a gradient scheme for any of your other vector fields, you will have the default scheme applied to it automatically. In this case, we have Gauss linear. For both, we have Gauss linear. I'll talk about this as well. And the next option we have is grad P. So this is your gradient scheme for pressure. And now again, over here, it's not necessary that it will only be for pressure. Now in the icoform case, you only have pressure. But in a simple form case, you might have some additional fields that you want to compute or you want to see properly. So again, I'll open each of those files and show it to you. So over here, now under grad P, if you are specifying, say, Gauss linear, or you're putting a limiter, so whatever setting you specify for grad P, it will override the default setting that you have specified. So say my default setting was Gauss linear, and for grad P, I am adding a limiter. So I would say limited Gauss linear. So for the pressure gradient, it will specify or it will use whatever setting I'm specifying in that particular type. Okay. So always keep in mind, if you're putting it as default, it will take the default thing. So if I were to put the same thing, I can just remove this line and it will make no difference because the default setting is set to Gauss linear. Okay. Now, coming to the setting that you're choosing. So we have multiple options. Again, I'll show it to you in a bit. So the Gauss linear, or just take the word Gauss. Okay. Now the Gauss is using your Gauss gradient scheme. Now this is a whole topic in itself. That is why at the end I have added a few videos. You can check that out. So to keep it very simple, you have a Gauss gradient scheme that is being solved by using this keyword. In the backend, there are codes that are running that particular code, and you're just using a keyword over here. So the Gauss is your gradient scheme, and for solving your or solving or going ahead with your simulation, you have to add an interpolation scheme. Okay, I will show you this particular equation in depth when we go to the div schemes or the divergence schemes. In that, I have added the proper equations and everything. So in that, it will get a bit more clear over there. Okay, for now, it uses the Gauss gradient scheme and requires an interpolation scheme, and the interpolation scheme here is linear. Okay, now there may be more options to it, but for very basic terms, you are using the linear interpolation scheme. Okay, I'll get back to this again. In div schemes, we have added all the keywords that are required. Now, the available options that are there for your gradient schemes. Now, the most stable one is Gauss linear, and your most accurate one is your least square. So again, least square method in itself is again another topic. That also link I have added at the end of the PPT. And there is another another option that is known as limiter, that, as I said, if I want to have a stable simulation using a fairly complex or an accurate grad scheme, I can add a limiter. So in this case, we have the cell MD limited Gauss linear 1.0. So this is just a limiter that you can add for stability. Again, there may be more options. You can change all of these parameters. I will show you how to search. Like if I want to search for grad schemes, how many limiters are available in my particular OpenFOAM version. I'll show you how to list that out also through the terminal. You can do that. Okay. Okay. So moving on to your divergence schemes. Okay. So now you're completed with DDT schemes. That was your derivative schemes. You're done with your gradient scheme. That was grad schemes. And now you come to div schemes. Okay. Now this is your divergence schemes. So by default, we have set it. Okay. So this is where you will add your approximations or methods for approximating your divergence integrals. Okay. In very simple terms, it does that. And you're again default, you're specifying none. So this forces us to specify divergence schemes for each of the parameters that you're listing. Okay. So this is essential. We don't specify, like in some cases you might specify a default divergence scheme, but it does not work for every field. So for vectors it is a bit different, for scalars it is a bit different, and for viscosity terms it's a bit different. So again, we'll look at that in a bit. So again, default it is set to none, saying that whatever you are specifying over here, you will have to specify for each of the fields. So for vectors, you will have to specify one. For scalars, you will have to specify one. Okay. Now, your div phi u. So that is your integral or divergence integral for 5 times u. Now phi over here is your flux, and for incompressible flow, your flux is equal to your velocity. U is your velocity, and yeah. Again, over here you have your Gauss divergence theorem. Again, as I said, in the previous case also what you saw. So in this one, you have your equation over here. You have your divergence part. So this one in simple terms converts your volume integrals to surface integrals of divergence. So over here you can see that we're integrating the divergence divergence term with in terms of volume, whereas over here you're integrating it in terms of your surface integrals. Okay, so it just converts that. And for to convert this or to find your surface integrals, that is where you require your interpolation schemes. So this is why you require Gauss and linear. So linear is your interpolation scheme, Gauss is your divergence. It's using a divergence theorem or gradient theorem, whatever you want to use. Now your divergence schemes, it is the most important part, because you mess this up, you will not get good enough results, or you might even have simulations crashing. Okay, so your divergent terms are critical to to are critical for your accuracy and stability of a simulation. Okay, so just blindly don't specify anything. Again, I can show you how to specify for a particular vector what are the options, for a particular scalar what are the options, but again you need to have some knowledge, or you need to know what you're doing. Otherwise you will just end up specifying something and you will not really learn anything, and you will get some results, it might not be even physically accurate. So always cross verify it with whatever paper you're referencing, and then only put your equations properly into this. Okay, now these are some of the available options. Again, most accurate on the top, you have most stable on the top, you have an accurate option as well, Gauss linear. You have stable solutions as Gauss upwind. You also have some commonly used ones, or you can say average options. Those are your Gauss linear limited 1.0. The second one is Gauss linear upwind, and over here you can specify your grad scheme. So in our case, we saw for grad scheme we had one for default and we had one for grad P. So over here, if I were to specify it in this case, I could specify it as Gauss linear upwind and then grad P. So over here, it is using the gradient schemes or the options that I've given for gradient schemes to solve it in your divergence schemes. Okay, so they both are linked to each other, so you can solve it based on that as well. There are some additional, I wouldn't say common, but it's a more of an advanced thing. You have Gauss van Leer. So for multi-phase simulations, you'll see it in a bit that they have used the Gauss van Leer options. And again, over here for steady state, or if you're solving for any steady state simulation, like simple form or something like that, you will have the keyword bounded. So this is just an extra term that you add to aid the convergence criteria in your whole simulation. It does not cause any disturbance in your solution, but it again aids in convergence. That's why we use it. So if you open any of the simple form FE solution files, you will find that the bounded keyword is always there in div schemes. Okay, now these are some of the available options, some of the more common selections, okay, that you have. So as I said, default none, that is why that is where you will specify for each of your field. So again, over here we have some additional fields as k and epsilon. Over here you can see, so those are your turbulence modeling parameters. So k, epsilon, omega, all of those things. And the very long equation that you see at the last, that is your viscosity term. So it's very simple to find out your viscosity term. It's the longest equation present in your div schemes. Okay. So we've seen div 5. This is for velocity. These two are for turbulence. So you can say that these are scalar. This is a vector, and this is your viscosity terms. Okay. So for vectors, the you can say the most commonly used or the recommended div schemes or the divergence schemes are Gauss limited linear V 1.1, 1.0. So over here the V stands for vector, and for other fields like scalars in particular, you can use the Gauss linear limited. This is without the V. Again, there are multiple options. It's not necessary that you have to use this particular thing. Sometimes it depends on the simulation that you're solving. So if you're solving a multi-phase simulation specifically, you will have some additional files as well, like you have alpha.water, or you might have alpha.air, something like that. So in those cases, you have additional parameters. So those might require very specific divergence schemes. Only then it can solve it. Especially it depends on the derivative schemes also you're using. So all of these are interconnected to each other. So unless you know what you're doing, I would say stick to the recommended options. If you know or you want to explore these, you can always change something. You can check those out. There is also an open form documentation in which they have changed the divergence schemes and shown you how does it affect the accuracy and stability of your simulation. That documentation link also I have added it at the end of the PPT. Okay, so just check that out. And lastly, we have the viscosity term. Again, for viscosity term, the recommended use is Gauss linear. It's the most stable one. That is why we use that. Again, if you want to explore other options for this, you can check those out as well. Okay, so at the bottom, just remember, if your accuracy is increasing, your stability is decreasing, and vice versa. Now, then after your DDT schemes, div schemes, grad schemes, you would have Laplacian schemes and you would have interpolation schemes. Now, these two are interdependent on each other. For that, you have to first know SN grad schemes. So in this case, SN grad schemes is your surface normal gradient schemes. Okay, to put it very simply. So this is where you would add your approximating or your methods for approximation the or approximating your dot product with respect of dot product of your variable to your surface normal. So the relation is given over here. So over here you have some options as well. So before going into this particular option, you first have to know what is non-orthogonal angle. So this is the only parameter that is based on your mesh. That is why we say that when you're doing CFD simulations particularly, you have three very important things you have to take care for a good solution or at least accurate solution. First is your mesh. So you need to have a good enough mesh, and by good enough we don't mean it should be looking good or it should have proper grading and all. There are also parameters as skewness, non-orthogonality, aspect ratio. So all of those parameters are very important when you're meshing. Only then you can expect whatever boundary conditions or whatever schemes you're using will be properly implemented in your mesh. So you need to have firstly a good mesh. Secondly, you need to have proper boundary conditions applied. Yesterday, Pranay specified or stressed on a lot of the boundary conditions that are or how they play a role in your CFD simulation. Again, boundary conditions and schemes, garbage in, garbage out. If you don't know what you're putting, you will not get proper results out. Okay, so blindly putting all of these parameters won't help you get an accurate result. So meshing, boundary conditions, and your numerical schemes, these are the three, or you can say the backbone of your CFD simulation. You get even one of these wrong, you will not get your results properly. Okay, So 90% of people ignore the last two, that is your boundary conditions and numerical schemes. And to some extent you can get away with it. Like if you're using the default selections in open form, you will still get good enough results. But again, if you're doing something extremely specific, like in multi-phase simulations, you have to do particle tracking on all of these. Or if you have if you have a simple bubble simulation, you want to capture that bubble properly. So in those simulations, knowing what you're doing or putting proper schemes are very important. Otherwise, you will not get results. Like a bubble may deform, or the bubble may not even show up in your whole simulation. So those are some parameters that you have to keep in mind. Okay. So now I spoke about the non-orthogonal angle. Okay. So let's see what exactly is that. Okay. So let's say that we have two cells. Okay. Now this is my cell one, cell two. I made this particular mesh using block mesh. Okay. Now these 2 points in red, those are my cell centroid. And if I were to draw a proper surface normal from both of these points, or you can say normal or perpendicular to the intersection of this point, it is 90 degree. So this particular section, or the surface normal in simple terms, will always be 90 degree or perpendicular to the face. And if I were to draw another line, say joining these two centroids, okay, so I'll draw from centroid 1, that is the bottom one, to the top one. So centroid 1 to centroid 2. If I were to draw this particular line, it would overlap my surface normal. Okay, so the angle between the line drawn between these two centroids and the angle between the surface normal is 0. So in this case, my non-orthogonal angle will be 0. Now let's take this particular example. Okay, now in this one, my top cell has been skewed or been deformed up to a certain angle. Okay, so now in this case, if I were to draw that surface normal, it's going to be perpendicular to this particular interface. And if I were to draw again a line from centroid 1 to centroid 2, now there's a difference, or you can say a deviation between these two vectors, or you can say these two lines. So this particular difference between these two lines is your non-orthogonal angle. Okay, so as I said, this is the only parameter that will be based on your mesh. So there are ways to even check that. I will show you in a while. Okay. Okay, so before going to the orthogonal part, I'll show you this in a. So over here, I have a very simple case. I just have zero constant system, and I just want to show you the mesh. So I have a block mesh in place. This is now for flow over a cylinder. Okay. So first I'll just source my OpenFOAM version. So I'll just click or type block mesh. Okay, I've created my mesh. I'll just view it in ParaView. Okay, so see over here, switch to 2D mode. So over here we have a simple cylinder. We want to find the flow over a cylinder. Okay, so I'll switch to mesh. Okay, now this is a decent mesh, I would say. You have proper grading and all of these things, but we are not interested in the grading part. Okay, we are interested in the skewness. So let's say if I were to take any random two random cells from this particular zone. Okay, so here it is proper 90 degree, or it's in parallel, you can say, two of the cells. So over here my non-orthogonal angle will be 0. Okay, but if I take something like this over here, for instance, so I have this particular cell and I'm taking this particular cell. Now if I want to find the non-orthogonal angle between this, there is a way in OpenFOAM. Okay, you have the check mesh option. So if I just type check mesh, so once you do block mesh, you can do check mesh. So this will give you some interesting parameters or some interesting variables that you have about your mesh. That's why you have to first complete your meshing and then you can do check mesh. This also works for snappy hex. So once you're doing snappy hex, you can always check whether your mesh is good enough or not. If something is not correct, or it's, let's say your non-orthogonal angle is too high or your aspect ratio is extremely high, it will just add over here an asterisk mark and it will say that mesh failed in this particular, or it failed in one particular area or two particular area. So it will give you an option. If say it not an option though, it will give you a keyword saying that it is okay or it is not okay. So over here we have the overall domain. So my bounding box, in simple terms, you can say your entire domain, computational domain. Then you have some additional parameters like cell openness, aspect ratio. You also have minimum face area, volume, and over here you will have mesh non-orthogonality, max, average. So over here we have to check the maximum angle. So in this case it is around 44.072. Okay. Now based on this particular value, you have to specify in your FV schemes. Okay. So now the simplest one. Okay, so if your mesh is uniform, like say our cavity case in which all of your cells are uniformly distributed and they are, you can say, parallel to each other, so you don't have that much of an non-orthogonal angle. Okay, so this particular keyword, it will be based on your non-orthogonal angle. So the available options here are based on that. So as I said, you have to check your max non-orthogonal angle. So if it is less than 0.5 degrees, so you can go with the orthogonal keyword. If it is less than 5 degrees, you can go with uncorrected. If it is somewhere between 5 and 70, you can go with corrected. And if you have something between 70 and 80, you can go with limited corrected 0.5. And if it's anything above 80, then it's better to go back to your meshing. So as I said, when you create a mesh, it's always good to do a check mesh to get an idea whether your mesh is good enough. It should not happen that you have created a mesh, you have set up all your boundary conditions, numerical schemes, everything. You run your simulation, you spent around 2 to 3 hours on running that simulation, and then you realize that your mesh was not proper. Correct. So it's always good to do a check mesh, get an idea of what exactly is going on in your mesh, and then go ahead with your boundary conditions, numerical schemes. Okay. Now this is your surface normal gradient scheme, SN grad schemes. So based on that non-orthogonal angle, you can specify any of these. That brings us next to the Laplacian scheme. Okay. Now again, your Laplacian scheme, this is where you would specify or add your methods of approximation for Laplacian integrals. Now this particular parameter is based on your interpolation scheme and your SN grad scheme. Okay. So over here, again, it's using the Gauss divergence theorem. Same thing, it's using surface integrals of dot product and gradients and your surface normal. So in simple terms, to break this down, this is the syntax of this particular block. So you will have your keyword default. That means for every parameter you want to add this. You have your Gauss, that is your theorem that is being used. Then you have the interpolation scheme, and then you have your SN grad scheme. So if you look here, you will have Gauss, then you have linear. So in your interpolation scheme, there is an option where you can change it to linear or to anything else. So in this case, we have set it to linear. So you can write over here linear, and over here, whatever was in my SN grad scheme. So in my case, it was orthogonal, because my orthogonal angle for the limit driven cavity case was around 0. So it is less than 0.5. So we can go with orthogonal. Now, if I were to add the same particular case into the mesh that I just now showed you, the flow over a cylinder, in that you saw that my mesh or my non-orthogonal angle was around 44 point something, right? 44.0072. So in that case, I can type or I can use the corrected scheme for the SN grad scheme. So that would change in my Laplacian scheme as well. So in my Laplacian scheme, I would write default, Gauss, linear, and over here I would write corrected instead of orthogonal. Okay. So as I said, that two of the parameters are based on your SN grad schemes, or they're interrelated to each other, and your SN grad scheme is the only block that is dependent on your mesh. So make sure that you check all of these things before you actually run your simulation. So this is the syntax. And lastly, you have your interpolation scheme. So your interpolation scheme is default linear. So in this case over here, you add a method to find the value of your variable at a face. So again, this also in itself, you can study a bit more about it. I'll not go too much into detail for this. So I can show you some of the key differences. After this, we will, okay, I'll show you this one. Okay, so now suppose you want to search something specific. in your FV schemes. So say someone would ask me that in DDT schemes, I want to know in OpenFOAM 2412 and OpenFOAM 9, what are the options available? Correct. Now I can't go opening each and every file. Like I said that in multi-phase there are something, in simple form there is something. So yeah, it's not feasible to open each and every file. So there is an option, or you can type of command, that is your foam search. Okay, so this is the syntax for it. You have foam search, then you have to add your directory name, then you have to add the keyword that you're searching for, and then you have to add the file name. Okay, now in our case we have, say, foam search. This is an example. So we have foam search, and in foam tutorials, that is in your tutorial file, you want to find a specific, type or an option for your div 5 schemes. Okay, so in div 5 schemes, I will first specify the block that it is in. So it is in my div schemes block, your divergent scheme block, and within divergent scheme, it is in the I want to find the option for divergence of 5 times u. So this is my keyword, and this will be your file name. So in FE schemes, this particular thing is located. Okay, so let's see this in action. How do you search something? So let's say you want to go to tutorials. Okay, so now this is your tutorial file. So you have multiple options over here, or you don't necessarily need to go to the tutorials files itself. So say I were to, okay, let's say that we are in tutorial files. So I can just do foam search. So the best thing about this particular command is you can do it from anywhere. So you don't have to be in a particular file or a folder to implement this search. So I can do foam search. If you ever forget anything, like what is the syntax or something, you can always type foam search -h. The -h stands for help. So you can just type foam search -h. Okay, this one it did not give. So let's see. Okay, let's open a new terminal itself. Let's open this one only. WSL. So again, we'll type foam search dash. Sorry, I did not source it. Yeah. Okay. Okay, there's a small typo. Yeah. Okay. So there was a typo over there. I typed the word search wrong. It's fine. So for if you ever forget the syntax, you can type foam search -h. This is the same for any command. So if you want to even find something related to simple foam, icofoam, you can type the keyword icofoam -h. It will give you everything related to that. So the H stands for help. So over here, it will give me the syntax. So I can type foam search directory keyword file name. Okay, you can try the second one also. I tried running the second command. It gave me an error. It said that couldn't find. So I went with the first command. Okay. So you can type foam search. If you're in OpenFOAM 9, you can type foam search -h to see what is the syntax for searching a file in OpenFOAM 9. Now this one is in OpenFOAM 2412. So this particular syntax is there. So let's clear this terminal. So now I would type foam search. Okay, foam search. Then I would type my directory, in this case foam tutorial. Then I would type my keyword. So in this case, under say DDT schemes, I want to find for default what are the options. Okay, so DDT schemes dot default. Then that is the keyword, and I would type my file name FV schemes. So it will take some time. It will search. So you can see it processed 626 files. That is, in 626 files, there were FV schemes. So you can't physically open all of those files to search these particular options. So you can see over here, we have for default itself, you have so many options. So I showed you that there is Crank Nicholson, there is Euler, there's backward. So there's backward one as well. There's local Euler as well. And in OpenFOAM, you will have an additional option of local Euler MPLIC. So those are all interface tracking. So you can check those out as well. So we had one of the sessions or a workshop session on multi-phase simulations on these particular schemes itself. So you can check that out if you're interested. So again, you have multiple options, and then you have in the end for steady state, it's simply steady state. Now, if I want to find out how common are these, okay, now these just listed out the options that are there. Say I want to find out how many times it has been used in OpenFOAM. How common is it? So I can type the exact same command using foam search. Just after foam search, I can space -c. So that -c just will give me a count of how many times it has been used. So again, it will process all of those 626 files. It will take some time. It will give me in the end. Yeah. So over here you can see that for each of these options, it has given me a count of how many times it has been used. So out of the 626 files, 333 times Euler has been used, 170 times steady state has been used, and you can see 2 times Crank Nicholson has been used 1 time. So you can see backward Crank Nicholsons, even though they are accurate, they are not uh, commonly used. So as I said, in very specific cases, you would require to use these particular schemes, but it is not every time you have to use it. So if you're just running a simple case to find out the flow physics of or something like flow over a cylinder, in that you're not really interested in understanding that much of a depth, so you don't require Crank Nicholson that much, so you can go with Euler as well. Or in a steady state simulation, now in steady state you only have one particular option, so you can use only steady state. So any case that was run using simple foam or has a steady state, so you have simple foam, you have buoyant simple foam, you have multiple options. So there are different solvers that are there over there. So each of those are using steady state. So this is a way you can find a particular keyword or an option for a keyword using this foam search option, and you can even find out how many times it has been used using the foam search -c. Now these are two ways to find out in a particular file in a particular location how is it going to be. And there are additional options over here as well. So there is the grep-r command, but to implement or to use this particular command, you have to physically be in that folder. So say now over here I am in my case file, okay, in my run directory within a case file, and I am able to search in the tutorial folder what options are there. But to use the grep command, you have to physically be in the folder that you want to search. Now in this case, I would have to navigate to my tutorials folder, and within this I would have to type grep-r, that is search all the directories, or to search a directory -r. Then I would type a word, say, or the keyword that I'm searching for. So I want to search for, say, simple foam. Okay, so I would type simple foam, and then I would add an asterisk. So in this case, it will list out everywhere where the keyword simple foam has been used. So over here, when it is searching, it will give me the file that is in. So in the tutorial folder, under incompressible, under simple foam, under backward facing step, under all run, over here we have the keyword simple foam used. So again, over here, you can use grep command if you're not sure where a particular folder or where a particular file might be located. So in that case, you can use the grep command within the tutorial folder, or in case you want to search a specific keyword in, say, the solver folder. So you can again navigate to the solver folder, type the grep command, you can type simple foam asterisk, and it will give you that particular file or the location of that file. Okay. So these are a few commands you can use. And now moving on to the solvers. Okay, now as I said, we already have a session scheduled for solver modification, so I'm just going to show you where your solvers or the solvers that you use every time, where are they located, the source codes, how are they written, where are they located, and how can you access them. Now the path for either of the versions, so if you're using OpenFOAM 9, 10, 11, 12, the foundation version, this is the path for your application, for your solvers. So the solvers will be under OPT, OpenFOAM application and solvers, whereas for any of the ESI versions, it would be under OpenFOAM, OpenFOAM 24. You know that it is in your user lib OpenFOAM and all. You can again go to your applications and you have solver. I'll show you where exactly this thing is. So again, over here, you can again use the grep command. So you can type grep-r. I want to search a simple foam keyword. Again, simple foam asterisk. Okay. So let's go to the folder. So say this is my, or I open the new one. Okay. So on the left hand side, I will navigate to Ubuntu. So again, if I want to search for OpenFOAM 9, I'll go to OPT. And if I want to search for 2412, I'll go to USR or user. So under user, I will go to lib. Under lib, I'll scroll down to OpenFOAM 2412. Now, usually when we come to this point, you will click on tutorials. So you have tutorials over here, and at the very beginning, you have also applications. So you can click on applications and you can click on solvers. So under utility, you have some additional parameters like any of the post processing parameters you want to do or any of the functions you want to check. You can always open these as well. So under the solvers, you have in OpenFOAM 2412, you have all these solvers. Okay. So for acoustics, you have a particular solver. For any heat transfer or any basic simulation you want to run, you have the basic solvers. So in this, we have Laplacian form, potential form, scalar transport form. So in this, you want to do any scalar specific simulations. So you have, say, scalar A and scalar B, and you want to find out the mixing of that. We also have a lab migration on that. You can check that. So in those cases, we have used the scalar transport form. Any combustion, compressible. Now in our case, we are fine with incompressible because all of us have used the ICO form case. We have used a simple form solver. So we have all of these options. Okay. I'll parallelly open for OpenFOAM 9 as well. So the reason why we tell you to install both of the versions is because of the solvers itself. So again, if you open solvers, so you can see these are this side. Yeah. So you see the difference in the amount of solvers that are present in the the foundation version and the ESI versions. So that's why we tell you that if you have anything specific or you want to do something at an industrial level or something that the industries are doing, you might not necessarily have it in OpenFOAM 9 or in the foundation version, but you might have it in the ESI. Sometime it might also happen that that particular solver is in your foundation version, but it might not be in the ESI version. So it's better to install both of these, create an alias, and switch between both of these as and when required. Okay, so let's close this one. So say I were to open the incompressible folder. So under incompressible, I have all of these solvers. So we usually type in the keyword icofoam, right? So if I were to open any of the icofoam solvers, sorry, not the solvers, but any of the tutorials, and I copy any of those and run the command, I'll do block mesh and then I will do icofoam. But we are just typing a keyword icofoam. How exactly OpenFOAM knows that where to source the file or what exactly is icofoam, right? So all of us might be familiar with simple programming, right? If you specify a variable, say x is equals to a, y is equals to b, and in the end you write over there x is equals to question mark. So you will obviously locate that x is equals to a, right? Or you can say that z is equals to x. So indirectly z is equals to x is equals to a. Okay, so in similar way, even OpenFOAM is programmed that way. You have keywords that you specify, and it will source all of this option, or not options though, but all of these codes that are already written in C, C++, and it will implement that when you just type in that keyword. So in this case, when we type icofoam, under icofoam we have the create fields and we have the icofoam source file itself. So this is written in C, so you can open this. You can't make any of the changes in this file because this is a read file only. So if you want to make any changes, you would have to create a user app bin and all of those things. So we'll teach you all of that in solver modification properly, that what files are necessary and how to change a file or how to modify a solver. Okay, so over here it's pretty basic stuff. You have some of the header files that you include. Then you have over here, as I said, OpenFOAM is designed for the finite volume method. So over here you would have your finite volume, your derivative, then you have your divergence scheme or your divergence parameters, you have your Laplacian parameters. So all of these you just now saw that we specified div phi u. So all of these things are coded in the back end. So we are just doing top level coding. It's not even touching this, it's not even scratching the surface. Okay, so over here we are just typing div phi and then we're typing Gauss linear. So in the back end you can actually search for Gauss, what theorem it is using, how is it implemented in C, C++ or in OpenFOAM, and what equations it's solving. Okay, so you can always check all of these things out. So I said under utilities you can check all of those things. Under solvers also, now all of these header files, now over here we have just mentioned all of the header files, .h files. So you can open individually under create fields or wherever the header files are located. You can go over there, open individually all of these files, see how is it programmed. So if someone is into programming or wants to do some developmental work, because it may happen that OpenFOAM may not have a particular solver that you are looking for. So in those cases, you would have to add your equation on your own. So say I want to add a heat term in the simple form solver. So I can add a heat term on my own. So I can put that. I just have to change some of these equations, and I can do that. Okay. So I'm saying that anything is possible in OpenFOAM. It's not a black box, so you can do the coding on your own. You can also use LLMs to learn or to understand what are these codes actually doing. So you can just copy this code, put it in Claude or put it in ChatGPT, and say that explain this code to be. It will explain it in detail, because at the end of the day, it's a simple C code, and all of us in engineering have learned C, C++ at some point. So again, it's not rocket science over here. You can code anything. That, it's all possible in OpenFOAM. Okay. So yeah, this is where your solver files are located, or your solver code files are located. So as I said, some key differences in the FV schemes. I have listed all of these. I've also added a particular file that mentions all of the options that are present. You can check that out. I've shared it already on the drive, so you can download that. So this one is for the cavity case, your icofoam case. This one is for your simple foam case. You can easily come to know that it's a steady state case by seeing the keyword steady state. And the last one is a multi-phase case. So this is your simple dam break case. So you can see, if I were to just show you now, whatever code you saw in the PPT was all for icofoam. So you already have seen whatever parameters are available for icofoam. So in simple foam, it's a bit different. So if you were to add the turbulence model for your divergence scheme, so over here you have phi k, then you have epsilon, you have also omega, and all of these are linked to turbulence. So dollar turbulence is just saying that there is a keyword known as turbulence on the top. Just refer to that. So whatever parameter I'm specifying in turbulence, it will access that. So in this way, you can also modify your codes, or you can modify your FE schemes. So say you want to add turbulence for each of these. So if I want to change something, I wouldn't have to change individually for all of these three parameters. I just have to change it once over here. So you can modify all these codes as per however you feel fit. If you think that it is more convenient to you to just mention one keyword on top and then access that keyword throughout your whole code, you can do that as well. And a key difference in multi-phase simulation is that you will have something known as alpha. You can also check all of these additional parameters. We look at all of these when you're doing a proper multi-phase simulation. So you have some additional parameters as alpha dot water for interface tracking. You will have some additional parameters that you keep in mind for multi-phase, because in multi-phase you would have two particular uh, two particular phases, or you will have two particular things going on at a single time. So you will have also fluid. You might also have, you can say, two fluids. Say one is oil, one is water. So those type of simulations require some additional parameters. So those things are mentioned over here. So as I said, over here, see, over here under SN schemes, now the case that they have set up, it might not have a non-orthogonal angle of say 0 to 0.5 or less than 5 degrees. It might have something between 5 to 70 degrees. So they have used the corrected option over here. Okay. So you can open all of these files. You can try copying one file. So say if I were to copy the simple foam FV options into icofoam, how is that different? Provided the parameters are same. Okay, so you have to just keep in mind that it has velocity and pressure, because in this particular simple foam case it also has turbulence, so it will start searching for turbulence. So in case you want to try doing that, you want to copy say simple foam FV schemes into icofoam FV schemes and see what happens, you can open that. And the most simplest way, say you don't remember any of the commands that I have told over here. Okay, I say I forgot what is the command or what exactly are the options for in this particular case. So this was a simple icofoam case. So under FV schemes, I say I open this one. Okay, I don't know what two extra options might be there. So I can just you know the option that we always type is banana. Okay, you can type your name as well. You can type apple, orange, whatever fruit you like. You can type that and save this file. And OpenFOAM will throw an error. Okay, so let's open that file again. Yeah. Okay. So let's say I do block mesh. Okay, block mesh already done. I run icofoam. Okay, so it can't find a 0np folder. Let's rename this to 0. It may not run because I haven't changed any of the boundary conditions. So it may throw an error before that as well. Let's see. Okay. Okay, it's giving an error on that. So again, you get the idea. So say now in my case, I haven't set up the boundary conditions for this particular case because my fields are different. So you get the idea, right? So you can just type in your name, or you can type in any fruit, vegetable, or whatever is your favorite word. You can just type that in, and you can then just run the whole simulation. OpenFOAM will throw an error saying that this particular keyword banana is not in its repository, and it will list out all of the options that are available for this particular scheme. So for this particular scheme, what are the available options? It will list out all of that. You can then choose from any of those. Okay. So yeah, this is it about the numerical schemes in OpenFOAM. Again, over here, all of the documentation is available. So you can open one of these. So this is the ASI documentation on which they have mentioned all of the numerical schemes. Everything that I've explained so far, it's all listed in the documentation. So you can open that, you can read through it if you like. There is also a documentation on the divergence scheme. As I said, they had changed all of these divergence schemes to show how does it affect your stability, how does it affect your accuracy. So all of this documentation is available on the internet. It's available on OpenFOAM's user guide and user manual. So you can open that, you can check that out. Okay. So yeah, this was it about numerical schemes and the solvers, at least the basic of solvers.